All right, back to differential equations. In this video, I'll be discussing really just section M, unhelpfully titled differential equations. I mean, that's really what M and O and P are about. Today we'll be talking about how to estimate the solution of a differential equation. So previous video, we saw 3 ways to solve a differential equation, but we're also responsible for 3 methods to estimate the solutions to a differential equation. We'll cover 2 of those in this video. And we need to know how to do this because lots of differential equations we just can't solve with the methods in this course, but that doesn't mean that we can't get an estimate for them. The 2 techniques that we'll be discussing here are called slope fields, which is kind of a visual way to estimate a solution, and we'll come across a new piece of vocab called an isocline in a few minutes. And then the second technique is called Euler's method. I'm going to leave Euler's method for the end because it is painful, and also I think it makes a lot more sense once you understand how slope fields operate. You can get a sense for what Euler's method is about. Otherwise, it's just a whole bunch of numerical steps that don't really have any context. I want to begin again with a really simple differential equation that we definitely know how to solve. Y prime is equal to cosine x. What is y equal to? Okay, we all know that it's sine of x plus c. I want to show you this now as a slope field. So this is the slope field for cosine of x. And I want you to imagine that it goes on forever. I mean, Desmos is only really showing it within this grid, but you can imagine this pattern repeating throughout the entire xy plane. What a slope field is it shows us the slope at any particular point as defined by a particular differential equation. So we said, in this case, y prime is equal to cosine of x. So like when x is 0, for example, okay, cosine of 0 is 1. And you'll notice that everywhere along x equals 0, we see little slopes of 1. When x is equal to pi over 2, cosine is equal to 0. We can't really see, pi over 2 is not actually in this picture, but we could imagine that it's somewhere in between these two, so kind of where my mouse is going. So the slope field doesn't show every single point. It couldn't. Then it would just be filled up with, you would be able to see anything. But it just shows a bunch of points, usually in a defined grid of some kind. What's I think is very interesting about this is that you can actually see the answer to the differential equation, right? I mean, the integral of cosine is sine. And do you see sine curves in here? And not only that, but it's actually an infinite family of sine curves, right? Representing the fact that we have sine of x plus a constant. So I actually see all of those sine curves here in this picture. So already I think that's kind of neat. And the other thing that's nice about it is we can work with initial conditions in this way. So let's say we had an initial condition. We could then figure out a particular solution, sine of x plus 2. Well, even if I didn't know that the integral of cosine was sine, I could still draw a sketch of this curve. And when I say this, I mean, look, if I don't know that the integral of cosine is sine, then I don't actually know what this curve is explicitly. I don't know what its equation is. But I could still sketch it, because if I know that y of 0 is 2, all I have to do is say, all right, well, when x is 0, y is 2. And then I just follow the slope field and see where it tells each point to go. So this point, its slope was about 1, so I'd go up here to the next point. And then that one's a little bit less steep, so it should go somewhere up here more or less. And then I see the slopes are pointing downwards, so I'd start going down more. And then they appear to still be down, so I'd continue down. And then I see they're flattening out. And it's not an exact process. Like, no one's going to expect you to draw a perfect slope field. but you can easily get an estimate going, and you certainly know where the initial condition is. So anyway, you could imagine that, yeah, you could get like a semi-decent image of what sine of x plus 2 looks like if you followed those slope fields out to the left and out to the right. And that's really what the purpose of a slope field is. It's a way for us to estimate it, because then you could say, well, if that red curve is the estimate, then what is y equal to when x is equal to 10? And then I could look along my curve and I'd say, well, it's about, based on what I drew, it's about that there. Now that's a terrible picture, but the idea is, I think, sound. Let's take a look at another one. This is another very simple differential equation. I separate the variables and I end up getting that as my general solution for it. So now let's look at the slope field for y prime equals x over y. This is what it looks like. And again, you could like verify this by just choosing some x and y values and saying like, okay, what should the slope be at that point? Clearly, anywhere along the y-axis except for the origin, we should have a slope of 0. Of course, at the origin, then we'd be dividing by 0, so it'll be undefined there. We get this kind of weird grid happening. Let's actually graph this one. So here I've got the square root plus and minus the square root of x squared plus c. And we can see that as we change the c value, we're always getting a curve that fits the slope field really perfectly. So that's slope fields right there. What do we need to do with them now? Well, you might be asked to draw them, maybe. The AP has asked that a few times in their free response sections. I don't think the IB has ever asked it, but we'll look at an example of that. Drawing a slope field is just very simple. That's like kindergarten stuff. So you might have to draw one. You might have to estimate a curve, which I kind of just looked at, and then we'll talk about isoclines, as I said, in just a minute. All right, so let's look at this problem from AP 2005. Get that out of the way. The plan here, I've got 12 dots in the grid. So for part A, I just want to sketch a slope field at each of those 12 dots. I'm going to literally use this equation up here, and I'm going to draw a little slope determined by that function. And you can either do this mentally or you can really quickly just verify. You can jot it down in a table if you want to. Obviously, whenever x is 0, my slopes are 0, and when y is 0, my slopes are 0 also. And then just jot down the rest of these. Now, no one's going to like grab a protractor and make sure that these slopes are angled correctly. You just want to make sure that like they're positive when they're supposed to be positive, negative when they're supposed to be negative, and like generally speaking, getting more steep when they're supposed to be getting more steep. But other than that, don't worry about precision. Let's do letter B. Write an equation for the tangent line to the graph of f of x, whatever it might be, at the point x equals -1. Well, for this, we want to use probably point slope form. So then we work out what we know. We know that the y value is equal to 2. We know that the x value is equal to -1. And we actually know the slope. It's not obvious from the picture, but it was on screen a moment ago. That slope at that point was equal to 2. So that's the equation of the tangent line. So we can see that slope fields connect back to like core calculus in neat ways like that too. Anyway, part C I'm not going to do. That's just solving the differential equation. That's clearly separable. We don't need to talk about that now. Next, I want to discuss isoclines. So an isocline is just a set of points where they all have the same slope, same gradient. You could algebraically think of an isocline as a curve that looks like that. And this is h of x and y, meaning this is a function including x and y, and it's all set to being equal to a constant. Why? Because, again, h of xy is our derivative. So like in the previous example, I don't see an isocline here, but I have a derivative which is equal to a function of x and y. So if I found, well, we could describe the isocline of where that's equal to 0, and that isocline would look something like that. It would just be the axes. That's a boring isocline. Here's a slope field that has some more interesting isoclines. So they've chosen to represent 2 of them here, although that doesn't mean that there aren't more. The first one is basically identifying, okay, so when is that equal to 0? Essentially, when is our slope, when we have a vertical tangent line, when we have undefined slope. That's going to occur at all of the points along the red line in the picture. The slope in our slope field is going to be equal to 0, however, when the numerator is equal to 0. And we can rewrite that in that form, which we recognize perhaps as being a circle of radius 1 centered at the origin. So every single point along that greenish circle has a slope of exactly 1. And of course, I don't mean to say that every point on the circle has a tangent line like on the circle that's equal to 1. You know, clearly that, you know, slope of a tangent line there is not 1. However, if I take the x-coordinate, square it, the y-coordinate, square it, add those two together, that's when I get 1. Obviously, the line that we graphed has a slope itself of positive 1, but that line represents all of the points which have undefined slope within the slope field. So don't like confuse those two ideas. So I think just one book problem would be nice, and then we can move on to Euler's method. So you can see a slope problem question could be fairly lengthy. There's a lot going on here. So let's jump in. Part A, verify that y equals c blah 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 is a general solution for the, okay, so that just means like solve the differential equation, you know, like separate the variables, figure out the general solution. Okay, I don't want to talk about that. That's kind of dull. There we go. We've talked about this all before. Part B, construct the slope field. So we just talked about how to do that. We're going to do that with integer values from 0 to 4 for both x and y. So again, just using this rule, we're going to multiply the two coordinate values together. So you don't need to make a table. The book does it. I had done it. Obviously, you could construct this slope field just without it. Now I've got the answer to the next part showing up here. So pretend these curves aren't there just yet. Just take a moment and verify that the slopes of these little line segments match up with the slopes in this table. Okay. Part C, sketch the particular solution through 2, 1. So 2, 1, that's that point, and then you just kind of follow the slopes around. I like to think of it as like currents of air or water, and I'm just following where the current would push some object that was suspended in the fluid. I don't know, that's me. Part D, okay, verify algebraically that this curve is in fact this one, which looks kind of weird. No problem. That's just like we know the particular solution goes through 2, 1, so we're basically solving for C. That's all that part D is talking about. Nothing exciting. Now part E, draw the isoclines corresponding to K equaling 1, 3, and 6. That K value, you recall from a few screens ago, means we're going to set x times y equal to 1, x times y equal to 3, x times y equal to 6. Probably rewrite those as y equals in each case and just sketch those curves. Now those are all clearly going to be hyperbolas. So that kind of makes sense for these 3 curves that I'm seeing there. And in fact, yeah, we can see those are rewritten as y equals 6 over x, 3 over x, and 1 over x. And they're simply connecting the points with the desired k value. So the first one was k equals 6. Looking in my table, I've got 2 points where we could have 6 as a slope, and they're at 3, 2 and at 2, 3. And we see that that isocline does go through those 2 little slopes. Same thing with k equal to 3. I'll just show that one. k equals 3, whoops, no problem. It's going to go through those 2 points. It's going to go through 3, 1, and it's going to go through 1, 3. Same thing with k equal to 1. And again, besides going through those 2 points, you're just kind of estimating where it would continue in both directions. There's no need for perfection here. So that's slope fields and pretty much everything that we can do with them. Not a super common topic for the IB, but they have asked about it in the past. Next, we'll look at Euler's method, which is much more common to be asked by the IB. But I think considering it within the context of a slope field will help you make sense of what it means. So first of all, up at the top of the screen, this is in the formula book, but that's a whole lot of algebra noise. So let's talk about what that is saying. So here's a slope field, and before I discussed kind of imagining what would happen if we took a random point, you know, our initial value, and then just set it going through the current. And we could visually see it would go here, and then it would go kind of down this way, and it would end up like that. Okay, cool. What Euler's method is a numerical approach to doing just that. We still start with the initial condition, and then we, rather than drawing, we numerically, by using the coordinates of that point and by using what the slope is at that point, we move just a little tiny bit in this direction, and then we reevaluate. What's the slope there? And then we move a little bit in that direction. And then we move a little bit and move a little bit. It's very tedious. It's time consuming. Yeah, usually you end up having to do this like 5 or 6 times to get to whatever the estimate would be. So how are we going to move from one point to another? Well, it's all according to this rule up here. The x value is kind of easier to work out. So our x value is always going to be equal to the x value that came before it, plus some constant which is given to us in the problem. It's called the step length or whatever. That's just telling us basically like how far to the right do we want to move, because we're always moving from left to right. The y value tells us whether we're going to move up or down from there. And the y value part is slightly more complicated. Each y value is going to be equal to the y value before it plus that same step value multiplied by the f of x sub n, y sub n. That's the slope at the previous point. So you got to pay attention to where you're dealing with n and where you're dealing with n plus 1. Let's visualize this a little more. If we start down at the bottom at x sub 0, y sub 0, we're going to get up here to x sub 1, y sub 1. How are we going to do that? Well, the change in x is simply the first x point, x sub 0, plus h, where h is our step length. X sub 0 plus h clearly gives us x sub 1. To justify the way to get from y sub n to y sub n plus 1 here, let's consider that so the gradient is, first of all, defined as by our slope field. So we have some function of x and y. However, just using the slope formula, we can rewrite that as y sub 1 minus y sub 0 over x sub 1 minus x sub 0. But then recognize that this denominator is just h. So we can multiply both sides by h, and then we can add y sub 0, and we'll get y sub 1 equaling to y sub 0 plus h times f of x0, y0, and that's precisely what we see over here, except we put in 0 for n and 1 for n plus 1, etc. Anyway, we perform this. We grab a calculator. We're going to like have some decimals or whatever. We just do this once to get from our initial point, x0, y0, to x1, y1, and then we do it again for x1, y1 to x2, y2, and then we do it again and again and again. Let's just look at one. You'll see what I'm talking about. So here it is. And I got all the works there, but This is our differential equation. This is our initial condition. So we begin with right here. X sub 0 is 0, and y sub 0 is 1. And we want to figure out what the next point is. We're told that the step size is 0.2. Okay, so really the left-hand column makes a lot of sense. I mean, this is fairly obvious what's happening. So we're starting at 0, and then we're adding 0.2 to get to 0.2. And then we're going to add another 0.2 to get to 0.4. We're going to add another 0.2 to get to 0.6, again to 0.8, and again to get to 1. And we're going to stop there because we're asked to estimate y of 1. So in this problem, it didn't tell us how many steps to use, but we can easily work that out because we want to get from 0 to 1, and the step size is 0.2, so obviously we're just going to use 5 steps. As for the y values, we start with 1, and then using the formula, our next y value is going to be 1 plus 0.2, that's our h, and notice that that doesn't change in any of the other lines. H is never going to change. So we got 1 plus 0.2 times 0 plus 1. Where does the 0 plus 1 come from? The rule is x plus y, 0 plus 1. We simplify this expression and we get 1.2. Now I want to find the next y value. It's going to be 1.2 plus h value doesn't change. And then I'm going to add 0.2 plus 1.2. Why is that? 0.2 plus 1.2. Simplify, we get 1.48. Next y value. We start with 1.48 plus 0.2 times 0.4 plus 1.48. That gives us 1.856. We do that again. It's 1.856 plus 0.2 times 0.6 plus 1.856. That gives us 2.3472 plus 0.2 times 0.8 plus 2.3472. Finally, we get an answer here, and then we're allowed to round that to 3 significant figures. It's 2.98. Do not round early on, otherwise that'll certainly get you a wrong answer. Save your rounding for the end. If you organize your work in a nice table like this, it's not going to be that bad. Like I said, the x values just kind of, those work themselves out very, very easily. The y values, you need to figure out where all the numbers are coming from, but it's not super challenging. And remember that this part is really going to be different in every problem, but that's just based upon whatever the initial, whatever the differential equation was. The rest of it is kind of the same thing every time. You're going to just take your preceding y value and plop it in as the first step for figuring out the next one, and you're going to just multiply your whatever your differential equation slope is defined by, multiplied by your h. And that's Euler's method. You can see why it's not fun to do. There's a lot of button mashing on your calculator, but that's all there is to it. So, hey, that's estimating differential equations. At least that's all the methods covered in section M. We still do have one more. I'm not going to do it in this video. I'll save it for one last one where we combine Taylor and Maclaurin series along with differential equations. I know, it's really exciting. It's been a while since we've seen Taylor and Maclaurin series. They're coming back, but not until next time.